Thanks a lot. I'm really happy to be here. This is my first time in hardwear.io. I'm ashamed to say that. But first time and starting very well. So yes, I will be talking about EUCLEAK, a new side channel attack. So it's not the same side channel than before. It's physical attacks, and I will go straight to it. So first, I need to define what I will call a secure element in this talk, and because this is very specific stuff. So a secure element is a chip, a hardware chip that is mainly used to generate and store cryptographic secret, and execute cryptographic primitives. This is all it does, and its main purpose is to get robust again. First, a remote attacker, what I call remote attacker, so an attacker that is able to communicate with it, but especially against physical attackers. Physical attacker is able to do exactly the same thing as a remote attacker, plus can take the chip, open it, put it inside a very powerful microscope and read the non-volatile memory bit after bit. So it's a little bit more powerful. There are three types of physical attackers. So side channel, fault injection, and then the invasive world where it goes very deep inside the silicon. We will talk about side channel here. So these attackers has to be hacked, need access to the component. While for the remote attacker, we finally using very simple hardware, using simple software, and using very simple communication protocols is quite enough. Sometimes you can even prove with formal methods what you're doing, so you have something that is quite robust after some time of development. For physical attacker, you need to develop specific hardware countermeasures and layers of security that you add up to get robust. You need also to have countermeasure at the software level and also as a cryptographic primitive level, right? And when you have done all this, and you have tested for many years that your secure element is starting to get resistant against such a powerful attacker as a physical attacker, then you can go to the common criteria scheme, certification scheme, and try to get the highest level of security, which is the fifth level, the above than 5 here. To get this stamp, you go to an independent secure lab, an ITSF, that will take experts and try to break in your implementation with all the means of a physical attacker. One of the key elements to have this stamp is to have closed source. Have your source closed means that somehow you are adding a new security layer to your implementation. Well, this is how the CC certification process works. It gives you more points when you are closed source. So right now, there is no secure element with a CC certificate that is open source. It doesn't exist. And there are 4 big players in this game. So NXP, Infineon, STMicroelectronics, and Samsung are sharing the market of these specific secure elements, meaning that chips that have this highest level of security. And the market is actually manifold. There are, of course, the smart cards, so passport, ID, transport, access, bank cards. These are the classical application of secure elements. This is where you will find them. Recently, we have a new application. It's a Bitcoin wallet, cryptocurrency hardware wallet and second factor authentication hardware wallet. These are applications where you also have very critical asset that you want to secure in a device that fall easily in the hands of an attacker. So physical, like secure elements is, helping there. But you also find them in smartphones for paying mostly, but not only, also as root of trust. In computers under the form of TPMs, these are secure elements. And in fact, everywhere that you will need to secure yourself against a physical attacker. And then you will implant these secure elements at the root of your system. Well, the EUCLEAK attack that I will present here it's in this world. We are attacking secure elements from Infinium on the signature primitive using side channel. We will reveal the crypto countermeasures and implementation, and we'll do that inside the second factor authentication hardware token from Yubico. So this is my presentation. I will first introduce the products and the side channel setup, and then we will go a little bit deeper inside the technicalities of the attack. Finally, we will come back to... It's not working? No. Yeah. That is real. It's back on. Alright. Yeah. And then I will discuss the impact analysis and then conclude. Yeah. So our target will be the FIDO hardware token. So what is FIDO? Is a protocol for second factor authentication. It's like this USB token you have to you need to plug them to your computer or smartphone when you log into a web service like Google account or Facebook. This FIDO protocol is based on the elliptic curve digital signature algorithm, the CDSA. And what it does is mainly generate secret key pairs and sign challenges. This is all it does, actually. So secure elements are, they are a good fit there. In 2001, Ninja Lab released a side channel vulnerability in another FIDO token from Google. So we call the attack a side journey to Titan. And the FIDO token is a Titan Google security key. And we found a side channel vulnerability in the ECDSA implementation that allowed to extract the secret key and clone the device. And when we did that, it happened that the secure element that we attacked, it was from NXP. It was from the P5 family of NXP, and it's quite an old secure element. So we just understood that more recent FIDO token were based on other secure elements, and in fact, most of them were based on the SLE78 from Infinium. And now, the leader in FIDO hardware token, Yubico, has all its FIDO token based on this secure element. So this what drive this research. The SLE78 has a cool feature that it integrates, some version of it integrates the USB stack. So you only need one component to build your security key. When with an NXP1, you needed two components. You needed the secure element and another one to handle the communication, right? To study this SLE78, we actually needed a training device because the FIDO protocol allows you to generate key, but never to extract them, of course. But you also are not allowed to generate a key and then push it into the key, a secret key, and then push it into the security key. That's not allowed. And for building an attack, finding a vulnerability, it's cool to be able to know the secret key at least to train, right? So we found this open Java card from Feitian that embeds SLE78. It's not exactly the same version of the hardware, not exactly the same version of the CryptoLib, the ECDSA implementation, but yeah, it's good enough. It looks like this. This is a smart card, so we open the rear of it, so we have access to the die, and we put it into our side channel bench. So what you see here is a custom smart card reader. It's actually, the board is developed by Ledger, a hardware wallet developer, and it's meant for side channel analysis. So you have your card there, and on the right picture you see our probe. So it's a electromagnetic probe that is put on top of the die. And while the SLE78 is computing signature, we observe the electromagnetic radiation of the chip. And it looks like this. This is a ECDSA signature on the Feitian Java card. So to understand this trace, we need to get back to what is ECDSA, right? So for those that know ECDSA, it's quite simple. For the others, you just need to know a few things here. You need to know that for a signature, you need a secret key, that is D, and a message, which is H. And at each signature, there is a random nonce, K, that is generated. It's called the ephemeral key in ECDSA, and its knowledge is as good as a secret key. When you know a K value for one signature, then you can compute the secret key. And the other way around, if you know the secret key, you can compute the nonce that was generated for a given signature. And this nonce is manipulated twice inside the signature algorithm. It's the line where you see the scalar multiplication. So it's K times G, a point on a curve, and it's the most time-consuming part of the ECDSA computation. So you have this computation and the second one in the inversion. It's a modular inversion in the last line. When you compute S, the output, one of the two parts of the output of the signature. So this is the modular inversion that we'll attack here. I highlighted that there is another modular inversion of Z here. Z is also a random, and it's used for side channel countermeasure actually. But what's important here is there is a second modular inversion. So let's get back to the trace. We have this we have this signature that starts by randomly generating Z, and K. And then this is a huge scalar multiplication that takes all the time of the computation. And at the end, the output of the signature is computed. If we zoom into this, we have this end of the computation. And here you have the two modular inversions, the inversion of Z and the inversion of K that have to happen there. And this is the longest part of this end of the computation. So identify this computation is quite easy and quite straightforward. So you can see these two large patterns. They are corresponding to the modular inversion. If we zoom into one of these modular inversion and we have a look at what it's made of, the side channel trace, you can see easily that it's an iterative process. So we can see that there is a pattern that is repeating itself ever and ever. And sometimes there's long iteration that usually there are short iteration, and then sometimes, it happens that there are long iteration. But what you can do, what we did is first detect them automatically and count them, because it gives us some like general information of what is the algorithm running here. And in fact, the average number of iteration match pretty well a standard modular inversion algorithm, which is the EEA, the extended Euclidean algorithm. This is the implementation of the extended Euclidean algorithm. Is quite simple. What you have to know is that there was these two intermediate variable R0 and R1 that are updated at each iteration of this while loop. And the while loop starts with a Euclidean division of R0 by R1. So the number of this iteration of this while loop correspond in average pretty well to what we are observing. But it doesn't match one for one. Like if I take one nonce value and I inverse it using this algorithm, the number of iterations won't match exactly what I observe for this specific K. And this might be because K is protected. So somehow instead of inversing K, they are inversing something else just to make the attack impossible. To really understand what's going on, we had then to get deeper and to study the inversion in a more easy way. We studied the ECDSA signature verification scheme, because this scheme also have modular inversion, but it does this modular inversion over public values. So the Infineon developer might not need to protect this value for the inversion. This is the side channel trace of ECDSA signature verification, and we can find the steps where the modular inversion are executed, and the modular inversion of S, which is a public value. And when we zoom again inside it, we find again all what we had found in the signature. So we have, we really are looking at the same process here. And this time it matches. So this time when we simulate the inversion of S and when we look at the number of iterations here, it matches. So we really identify the algorithm here. Also what we learn is that this long iteration actually have something to tell us about the inner computation. The inner value of R0 and R1 is actually related to the value, the different binary length, the binary length difference between R0 and R1. So for this iteration, we already have some information just by looking at the trace. And in fact, when getting a little bit deeper in observing the traces, so here you have only a single iteration. There's an odd iteration and even iteration. We have it at the beginning of the iteration, we have a part of the trace that changes in size, in length, in timing, when proportionally with the binary different, the binary length difference of R0 and R1. So that's great, because we just finally identified that this is the EEA executing. And also we already have a timing leakage. So at each of these iteration line 4 here, at each one, we can extract the binary length difference of R0 and R1. This is already something we get from sidechannel. So back to the signature algorithm, we have these countermeasures. So we expect it to be masking, a multiplicative mask. It goes like this. So K, instead of being manipulated directly, it's manipulated times a mask M that is generated on the spot. And it produces K prime. And then K prime is inversed using the EEA. And then if you want the inverse of K, because this is what you need at the end, you just re-multiply the inverse of K prime by M. And then you're done. So it's a pretty cheap and interesting countermeasures, and it's a very strong one. If you have a mass that is very large, well, as large as K, then you're done. Having any information about K prime gives you no information about K. However, if for some reason you choose M to be small, then it might be able, you might be able to brute force it. And why would you choose M that is small? It's because generating randoms is costly. So the developer might want to have a mask that is smaller in order to be less expensive. So we made this hypothesis and try to validate that the mask is small. Otherwise, we can just stop this work. We are going nowhere. And we are just betting on the fact that Infineon here choose a small mask. So what he did is take the first 10 traces we had, extracted the information we could, the length difference for each iteration. And for each of them, we knew the scala, the nonce K. We brute force the 2 to the power 32 mask for each of them. And for each of these masks, we simulated the EEA, we simulated the leakage, and tried to match what we observe. And it ended up in using the Pearson correlation to distinguish masks from bad ones. And at the end, for each of the first 10 traces, we had a single mask that popped up, and all the other ones that had very low correlation. So we are quite, sure at that time that, Infineon did choose very small mask, 32-bit ones actually. So that gets this project continuing. And so to sum up, we have this timing leakage on the EEA, where the fact that the blinded nonce is only blinded with 32 bits. So if somehow we can extract the blinded nonce, we can compute it. Then we would be able to compute the nonce by brute forcing the mask and then get the private key. The question is, does the timing leakage that we have found is enough information to reconstruct the input of the inversion? And it's not. Well, we didn't find any attack doing this. We built a generic attack process that didn't work because we believe, but we are not sure, we believe that the extracted information is not enough. We don't have enough leakage. So we have to get deeper into understanding the leakage. And this is the most time-consuming part of this work, has been to get back to the traces and try to find something else. You can see here it's a superposed iteration, like there is a 100. So there is at the beginning this leakage that we have already identified. What you can see is at the end of the iteration there is something blurry, like there is something that is moving, and it might be information that we can capture. It can be sensitive iteration, and this is what we try to extract. And this process of extracting, understanding what's going on here was pretty long, but it ended up in reverse engineering the Euclidean division algorithm that Infineon implemented. So it's here, and understanding it allowed us to bridge the gap between the timing leakage that we saw and the internal variables. So this is at the end the information that we can extract for each iteration. It's the binary difference length of R0 and R1, but so the number of loop of this while loop inside the division algorithm and some internal state of the division. So we have this improved timing leakage now. We have this fact that if we reconstruct the blinded nonce, then we will be able to attack. And now we have enough information. So we build this new attack on the EEA that takes the information that we extracted, and we were able to rebuild the input of the inversion just from looking at the traces. So we were quite happy. The attack itself is not described here. It's everything is all the details in a write-up that we published on our website. So we applied this attack on the YubiKey. So back to the original target of our work. So we took a YubiKey 5C UI and we put it inside our side channel bench. And we observed the side channel execution, found back the pattern of the modular inversion, and found back the different information we needed. So we could validate that the implementation is exactly the same as in the FIDO case, and that we had all the information we needed. The slight difference here is that we don't know the secret key. So to validate the attack, we have to do it to the end, right? So what we did is acquired 200 side channel execution tries of the ECDSA signature. We selected 6 that look better than the others, so the details are in the report. And for all of these 6 execution, we extracted the leakage. So for each iteration of the EEA, we extracted the leakage that I identified before, and this, in a semi-automated way. And then the attack was successful for 5 out of the 6. So for 5 of them, we extracted the blinded nonce. From these nonce, we brute force the mask to get the nonce, and then the secret key. For all these traces, the secret key is the same. So for the last one, we could roll back the study to look what was the problem. Now we have the secret key. And it was from errors in extracting the leakage. It's not something that is so easy to do, and I did it almost by hand, so I did error there. I think this process should be automatized and could be much more robust, and error could be avoided. But this is not our purpose here. Purpose is to do a proof of concept of the attack. So now let's move to the impact analysis. When we were able to attack the YubiKey, we were pretty happy, but we actually didn't know so much about Infineon security microcontrollers and the ones that are certified, right? So we had to understand the certificates and to extract from them the information needed to get a picture of what are Infineon security microcontrollers. So we built there is in fact 4 big families of them, from the older one to the more recent, and the 2 products that we attacked here, that we analyzed, are from the old family, the 90 nanometer family. This is SLE78 family, actually. But we found out that there were new version of the security microcontrollers of Infineon, and we were wondering if the vulnerability was still there in the new implementation, in the new versions. And fortunately, we found that some of the products in the new families are available to test. So in the second one, in the blue one, we had this Optiga Trust M component, which happened to be pretty available through DevKit board. You have the source code that it's necessary to talk with it and to run ECDSA commands. On GitHub, you have everything. So we bought one board, we put it inside our side channel bench, and long story short, we could validate that the leakage is the same. Like we can show that the implementation didn't change at all, and that we could find the leakage again. In the even more recent family, which is now based on ARM, the Infineon moved from their proprietary microcontroller on 16-bit to ARM versions, and so the Aptiga TPM now, so it's a TPM, is based on this in this family. It's a 40 nanometer die. We could buy a DevKit board and put it inside our side channel bench. And again, we could validate that this is exactly the same implementation. It didn't change. The side channel leakage is weaker. It's harder to exploit, but at least the implementation didn't change. Finally, for the last family, it's not possible. It's too recent. The first certificate was out this year. And there is no product that we know of or that are accessible to us that is based on this component. So somehow we concluded that all cryptolib of Infinium are affected by this vulnerability. And this means that this cryptolib went for like more than 80 certifications at the highest level in common criteria for over 14 years. And this leads to the conclusion of this talk. So the attack requirement very fast is you need a system that have critical assets where a physical attacker can access the chip handling this asset, and these assets are manipulated by a security microcontroller from Infinium and Infinium cryptolib. This asset must go through a modular invasion, like in ECDSA, for instance. If a physical attacker has access for a few minutes to the package of the Infinium secure element, then it can extract the side channel traces and then exploit them in an offline phase. So, if I get back to the big picture of EUCLEAK, in fact, the impact analysis tells us that all Infinium security microcontrollers are affected, which makes all common criteria certificate from Infinium just fall apart, and it goes well beyond second factor authentication products. It's everywhere. You have Infinium products everywhere. So the mitigation, I will just say a few words. The Infinium implemented the simple mitigation, which is increasing the mass size from 32 bits to the size of the elliptic curve, which is the good thing to do, and also a very fast implementation patch, right? They did that in few weeks after the start of the responsible disclosure. And I want to finish with the project timeline. So the project started in early 2022, where we identified the first leakage and the size of the mask, but then has to stop, and we waited. We had to wait for a long time before having enough time to continue. In mid 2023, the generic EA attack was built, but it ended up in a failure because we didn't have enough leakage. And then early this year, we could do the full reverse engineering of the division algorithm of Infinium, get all the leakage, and then ended up with an attack success. We went in a responsible disclosure with Yubico Infinium, but also the BSI, the German agency that certifies this chip. And during that time, Yubico released a firmware update for their YubiKeys, and they changed, they switches from the Infinium cryptolib to their own cryptolib. So they had their own cryptolib ready to ship, and this happened right at that time. It was a bit weird, but then they switched the firmware at that time. Infinium cryptolib was patched during this responsible disclosure, and at the end we published our work in a long write-up on our site. And now we are at hardwear.io, almost 2 months after that. So what happened between the publication and now? Yubico released a security advisory right after our publication, listing all the products and all the firmware versions that are affected, and even more that we actually envision, and what are the mitigation and so on. The BSI, so the German agency that certifies the Infineon chips, released a small public post in German saying that a click happened. There was no public statement from Infineon whatsoever since the release. And in fact, the single information we have from the CC scheme, the common criteria scheme, and Infineon is the update of CC certificate, which went pretty fast. What is interesting about this certificate update, so I take the first one, which was actually issued by the Dutch scheme, is that they recertify the chip, keeping the old cryptolib version unchanged. So the affected cryptolib version doesn't change. They recertify them as it. What changes is the user guidance of this cryptolib. But the user guidance of the cryptolib are secret. So we have no access to it. So we don't know, we have no idea, we have no way to know exactly which are the cryptolibs that are affected and which are not. To know that, you need to have access to the user guidance. And they did this for all the most important, I guess, security microcontrollers. So there are 4 out right now. I guess it will continue to cover all the security microcontrollers. But since we don't have Infineon statement saying this cryptolib version is affected and this is not, this is what we understood. So it's not an official statement from Infineon. It's just we believe that it could be interesting for the public to understand, to know what are the versions that are affected by the attack and what are not. So we again went over the certificates and extracted the different version and to put it there. Okay. And that's it for me. So thanks for your attention. If you have any question.
Thank you, Thomas, for the great research and I wouldn't underestimate it to impactful research, right? Do we have questions in the audience? Yes.
Thank you very much for amazing presentation and amazing work. So just to be sure, so no certificate was invalidated?
No.
Okay.
No, I think they don't know how to do that.
It is happening.
This is not part of the scheme. You cannot...
Well, I've seen certificates that were getting invalidated before, so... But okay, that's... but I don't know for what reasons, of course. Another question, so just out of curiosity about the first inversion of Z, did you have a look whether it was protected or... Of course, impact is smaller, but there is still probably some impact.
Yeah, the inversion of Z is interesting. We could, I guess, we didn't do it, but it could be possible to get the input of the inversion. I guess it's not protected at all because it's something that is not so sensitive. It is, but not directly like the key. That's the nonce. It's if you want to build an attack, you will have to do this for many traces. And for the nonce, you only need to do that for one. So my guess is it's not protected.
Okay.
But it leads to a harder attack.
Harder attack, but simpler this leakage part, I guess, because there is no brute force. But okay.
It's nothing yet.
There was no need for that now.
Yeah.
And about the countermeasure, so you mentioned that they were extending the blinding. So they were not going for the constant time implementation of the inversion?
No, I guess the easiest was the better.
Okay.
I mean, of course, if they wanted to have a patch fast, this was the easiest way. And it's pretty strong. I mean...
Yeah, of course.
Yeah, it works.
Thank you very much.
Okay, we have another question here. We had it.
Thanks for the presentation. It's like really nice research. But I have a question. You mentioned that like for that NXP chip has like highest CC certification, but I don't think so, because the highest level is like EL7, and in CC it's like only maybe 3 devices are already certified, and for doing that you actually need access to the source code. And I don't think the NXP went to the high level. So
yeah, it does. The EAL number is an aggregated number in CC.
Yeah,
and one of the source of this aggregation is the AVA1.
Yeah, but our one is like vulnerability assessment part.
Sorry?
Our is vulnerability assessment part of the certification.
Yeah.
It's like practical tests.
Yeah.
But also like it has like all like, how to say, access to the source code is also part of EL7.
Yeah. But it's also part for AVA1 5. You actually need
it's different discussion, but like, But I mean, like, I don't see like they had any EL7 certificate from CC before.
You don't need EL7 it won't change the level of security of your chip.
Yeah. Okay. Yeah.
All right. Thank you. Do we have any other question? Yes, we do. Thanks.
Hello, thank you for your interesting presentation. My question is, could you explain in some words more the ways of mitigations which you presented, which you shown on some slides before?
Yeah, I went fast on that. So there is this mitigation from Infineon. You get that right, huh? So after that, there is other way of mitigations. The question is about Infineon. Yeah, okay. They just changed the mask. You remember the mask was 32 bits. It's a multiplicative mask of the nonce, and they increased it to the size of the elliptic curve. So for the FIDO case, the elliptic curve is 256. So they increased the mask size from 32 bits to 256. So it means that somehow they are generating a larger random. This must be a little bit more costly, but maybe not. And they use this mask. And doing this, you can have an inversion algorithm that is completely giving side channel not robust. It can be completely vulnerable. It's not a problem. It's not a problem because the mask nonce gives you no information about the nonce itself.
Thank you, Thomas. Do we have any last question for now? Yes.
Thanks a lot. Very impressive work. So you showcased ECDSA here. Did you look into any other of the other crypto primitives such as EDDSA or RSA implementations?
Yeah, so EDDSA is quite easy. There is no modular inversion in this scheme, so there is no vulnerability with regards to EUCLEAK. Okay, and RSA it might be because there are modular inversion, but we didn't. Yeah, this is for future work maybe. Yeah.
Thank you. Thank you, Thomas. Let's give another round of applause for Thomas.